Hello, welcome to StudySync. In this series of algebra, we are coming to look at the introduction to complex numbers. As we saw from the beginning, complex numbers are made up of two components. A complex number represented by z is made up of a, which we'll be calling the real part, and b, which we'll be calling the imaginary component. And we've also described that complex numbers are the largest set of numbers that can be used in mathematics. Now let's move on to look at some characteristics of complex numbers. Now, complex numbers can be represented in the coordinate form. So we can have x and y. So x here represents the real component and y here represents the imaginary component. In the same fashion, when a complex number is represented on the Cartesian plane, the real component is the horizontal axis or the x-axis, and the imaginary axis corresponds to the y-axis. So any imaginary part is represented on the vertical axis and any real part is represented on the horizontal axis. So we'll call x the real component of z and y is the imaginary component of z. Now let's talk about what this I here is. I there means the imaginary unit. Now imaginary units can also be represented as a complex number in the coordinate form as 0, 1. Now what this imaginary unit is means that the real component is 0 but the imaginary component is unity, which is 1. That's why it is called an imaginary unit and denoted by I. Now it is also noted that I is equivalent to the square root of -1, which we'll be using in the later part of this video. The square root of -1 is I, called the imaginary unit. Let's look at some operations on the set of complex numbers like addition, multiplication of complex numbers. Now in the addition of complex numbers, so let's move on to the addition of complex numbers. So in the addition of complex numbers, if we have two complex numbers, let's say z1 and z2, then this z1 has its real part 1 and its imaginary part I. The z2 also has its real part and its imaginary part. In the addition of two complex numbers, the real components add and the imaginary components add. So a single complex number representing the addition of these two would have a1 plus a2, then plus b1 plus b2, then the I, where this is the real part and this is the imaginary part. Now in multiplication of complex numbers, let's look at an example. So we have the same z1 being given by a1 plus b1I and z2 being equal to a2 plus b2I. Then z1, z2 will be equal to a1 plus b1I multiplying a2 plus b2I. Now let's expand this and see how it will look like as in the normal expansion where we employ the distributive property. So we'll be having something like a1 a2 plus a1 b2I plus a2 b1I plus b1 b2I squared. Now we'll be looking at the powers of the imaginary unit very soon, then we can use it to complete this expansion. From the basic algebra, this is how an expansion of this will look like representing the multiplication of two complex numbers. So now every complex number, as you saw earlier, can be represented in the form. So let me write this: xy, which is a complex number, can be represented in the form x, 0 plus y, 0 multiplying the imaginary unit, which is 0, 1. So this is the real component, and this is another real vector, or let me just say a real vector multiplying an imaginary unit. The imaginary unit is represented by 0, 1. So this is another way of representing a complex number, and we'll use it less often. So in the algebraic fashion, z is equal to x plus yi, where x is the real part and y is the imaginary part. Now we've introduced the complex plane. Let's revisit the complex plane and its representation, representing an imaginary number on the complex plane. Now the complex plane, as I said earlier, the horizontal axis takes the real component of the complex number and the vertical axis takes the imaginary part. That's what a complex plane is doing for us. Now, as we already know, representing vectors is also the same way complex numbers are represented here. So when I have, for example, a complex number x plus yz, let me say x1 and y1. Sorry, let me make x1 plus y1i. Then I can say my x is here and my y is somewhere here. y1 and x1 is here. Then I can represent my complex number to and call here my z is equal to x1 plus y1i. So it's as simple as that. And the addition of complex numbers can also be visualized on this complex plane, where two complex numbers are drawn on this complex plane, and in their resultant, which is the addition of them, can also be visualized on this complex plane. So let's say, for example, we have two complex numbers z1 and z2 that are to be added. So let me call this z1 and that z2. If I add these two things, I'm expecting something like this with a bigger resultant, with a bigger magnitude. So let's call it z net. So we can draw some things. Okay, so now this represents z net, which is equal to z1 plus z2. Now the subtraction can also be performed also on the complex plane. Let's look at the concept of complex conjugate. Now when we say a complex conjugate, this is what we mean. So let's say z is a complex number represented by x plus yi. The complex conjugate is given a bar at the top. Now what this complex conjugate is simply negating the imaginary part. What that's a complex conjugate. And on the complex plane, when we want to represent a real number and its conjugate, it's basically, so if I have z, then the conjugate is going to be simply going to have the same x component, but this time the y component is negated, so it's going to look like this. So this is z bar, which is the complement. And what should you expect when you add a complex number and its conjugate? Then you should get a real number. And when you subtract a complex number and its conjugate, then you should be getting an imaginary number. So in a case of x plus yi, the complex conjugate is going to be x minus yi. When I should add these two, then the imaginary parts are going to subtract, leaving me with 2x. But when I should take the difference, then what's going to happen is that the real parts are going to subtract, giving me 0, but then the imaginary parts are going to add up. So y1 minus y1, which is going to give me 2y1. Okay, let's take an example on the algebra of complex numbers. So an example over here is, let z1 to be equal to 4 plus 3i and z2 should be equal to 2 minus 5i. Now we have to find z1, z2. So we are going to multiply these two complex numbers. Now let's look at what we get. So 4 plus 3i multiplying 2 minus 5i. Now let's employ the distributive property of multiplication over addition. So let's first take 4 and distribute it. So we get 8 minus 20i. Then take the 3i and distribute, to get plus 6i minus 15i squared. Okay, now I squared, as we'll see later, I squared is equal to -1, which are the powers of the imaginary unit. We'll look at it right now. So if I squared is -1, then we can simplify further to get 8. Let's group the real part. So if I squared becomes -1, then it means this term is a real term, and these two terms are the imaginary terms. So this is also a real term. So 8 plus 15, so negative times negative is giving us positive. Then minus 20i plus 6i, are going to get 23 over here, and then the imaginary part is going to give us minus 14i. So this is what we get for the multiplication. Now let's move on. So there are other examples on algebra of complex numbers. You can try adding them and other stuff, subtracting them, and play around with it. Okay, now let's look at some laws in complex numbers. So the first one we'll talk about over here is the commutative law. We've talked about commutative laws so many times since the beginning of this series. So commutative law simply means when you're adding two complex numbers, z1 and z2, z1 plus z2 is the same as z2 plus z1, and the other one is associative. So this is for commutative. Let's look at associative. So let's take three complex numbers, z1, z2, and z3. In adding these three complex numbers, we can add z1 and z2 first, and then we add these results to z3. It is the same thing when we add z1 to the results we obtain by adding z2 and z3. And of course, another part of it, we can also do z1 plus z3, then whatever we get, we add it to z2. This is all associative properties. Now let's look at distributive. Distributive too is employing the same thing. So the distributive law of multiplication over addition in complex numbers. Then here we should expect, when we have three complex numbers z1, z2 and z3, then z1 multiplying z2 plus z3 can be done by multiplying z1 by z2 and adding it to the result of z1, z3. So what's happening is that we have distributed this multiplication over here over the addition happening in the bracket. So if we distributed the z1 over the 2, so z1, z2 plus z1, z3. Now let's look at some laws that apply to conjugates, which we'll be calling laws of conjugates. So let's look at laws of conjugates. So when you are taking conjugates of complex numbers, there are certain laws attached that can even help you with smoother simplifications. Okay, now the first one is that when you have z1 plus z2 and you're taking the conjugate, is the same as adding the conjugate. So the conjugate of z1 plus the conjugate of what? Z2. Okay, now let's say z1 is equal to a1 plus b1i and z2 is equal to a2 plus b2i. Then let's try and prove this. So a1 plus b1i plus a2 plus b2i is equal to a1 plus a2 plus, let's put it in a bracket and call it b1 plus b2 or I. Now let's take the conjugates of all this. So let's take the conjugate of this result. So this is z1 plus z2. Now we start taking the conjugate of a complex number is by simply negating the imaginary part. So this is the result of the addition. Now the real part is a1 plus a2. The complex part, the imaginary part is b1 plus b2, and we negate that, we get b1 plus b2i. So this is the conjugate of the result we have. Now let's expand this to verify our identity. So we have a1 plus a2, then minus b1i minus b2i. Let's group the 1 terms and then the 2 terms. So we have a1 minus b1i plus a2 minus b2i. Now each of this is what? Now this is the conjugate of z1. Z1 is originally a1 plus b1i, but after we've expanded and taken the conjugate, we've gotten this, which is representing the conjugate of z1 plus, and this is also the conjugate of z2, and then hence the conjugate of z1 plus z2 is equal to conjugate of z1 plus the conjugate of z2. Okay, now the next law we'll look at is the difference, the conjugate of the difference. So to keep the video short, I won't go into the explanation of it. So the conjugate of the difference, z1 minus z2, is equal to the conjugate, the difference of the conjugate, which is z1 minus the conjugate of z2. So this is the conjugate of the difference, and this is the difference of the conjugate. So when you have this, you can do this, and they will give you the same thing. Now it applies also to multiplication and division. When you are taking the conjugate of a product, so the conjugate of z1, z2 is the same as taking the product of each conjugate. So z1 conjugate multiplying the z2 conjugate. It also applies to division. When you're taking the conjugate of this quotient, is the same as taking the quotient of each conjugate. So z1 conjugate divided by z2 conjugate. Okay, now let's look at the powers of the imaginary unit, which is I, powers of I. So I, as we said, is the imaginary unit. is given by in the coordinate form 0, 1, and we also made mention that in the algebraic fashion it is square root of -1. And we already know that square root of -1 is not a real number, it's an imaginary number. So when we square root of -1, then we should get that it should be what? -1. So I squared is equal to -1. So we'll build a pattern. So let's start. I is equal to I. Okay, so I to the power, let's start like this. I to the power 0. I to the power 0 is 1. Then I to the power 1 is I. I to the power 2 is -1, as we've just seen. Then we can continue when we have I to the power 3, which is I multiplying I squared, which is equal to I times -1. Then we'll be getting -I. So I to the power 3 is -I. Now let's continue. Let's look at I to the power 4. So I to the power 4 is equal to I squared times I squared, which is -1 times -1, which is 1. Now we are back here. So I to the power 5 will also give us I to the power 4 times I. I to the power 4 is 1 times I gives us I. So we are repeating back this cycle. So this is repetitive. So we can put this into a modulo. So we can put this into a modulo fashion. So we will take I to the power a particular number n, and we'll find what is going to give us. So depending. So we've ended at 3, and we've realized that for all going on, we are getting a repeated result. So the modulo we can use over here is in modulo 4. So in modulo 4, the greatest number is 3. So if n mod 4 is equal to 0, n mod 4 is equal to 1, n mod 4 is equal to 2, and n mod 4 is equal to 3. Let's look at what it implies. Then I to the power n is equal to 1. I to the power n will be equal to, so the repeated cycle. So we had 1, I, -1, and -I. So this one is going to give us I. Then I to the power n in this case is going to give us -1, and I to the power n in this case is going to give us -I. So for instance, I to the power 54 at random, 54 mod 4 is equal to 2. Hence I to the power 54 is equal to, then we come here, then we get what? -1. So that's how we deal with the powers of the imaginary unit. Thank you. I hope you like this video, and give us a comment for any concern you have. Don't forget to share this video as well. See you in the next lesson.